I decided I would say something about atmospheric seeing because it always seems pretty poor. And obviously, anything we do tends to be through the atmosphere, and we tend to have to look through the atmosphere to see anything we want to look at. Oh, it's not working. Okay. Okay, the definition of seeing is really how well we can look at astronomical objects through the atmosphere. And astronomers have proposed several seeing scales. Usually one is good and higher numbers are poor, but there's quite a number of these scales exist, but I won't talk about that today. Seeing, as you probably all know, is wavelength dependent, and it's worse at shorter wavelengths and better at longer wavelengths. So often you can get some advantage from using a red or an orange filter. The atmosphere, the Earth's atmosphere is about 300 miles thick, but most of it is obviously down towards the bottom in the first 10 miles or so. And as you all know, NASA spent $2.1 billion putting Hubble up and trying to avoid the atmosphere. So obviously they thought it was a good idea to try and do that. The basic problem is the atmosphere is turbulent. And so light passing through the atmosphere experiences refraction and depends how the atmosphere is moving in the different layers. This is an example of what I saw recently of Mars. And you can see here that the seeing is pretty poor and it's jumping around and pretty hopeless. And that's quite typical, I think, really. So the seeing can be affected by short range effects, and that can be within the telescope tube, or it can be in your observatory if you have one, or it can be close to the ground. So it's actually quite an advantage to put your telescope up above the ground. But the other thing that people talk about is long range effects, and it's in the layers of the atmosphere. All the layers of the atmosphere contribute to the turbulence. So inside the telescope, this is an example of if the mirror in your telescope is not cool enough, then you get these air currents, which you can see here. And obviously that causes refraction and disturbance of the image. And so it's important to cool your equipment down before you try and use it at all. The atmospheric effects, the long range effects are like this, that the incoming starlight is undistorted, the light wave is undistorted, and it comes to the atmosphere, which is turbulent, and it gets distorted. Now, if you have a small telescope, the distortion tends to be quite small, but the angular displacement you get at the end is quite large. If you have a large telescope, then there's large distortion, but strangely, the angular displacement of the image is quite small. So that's a kind of strange effect. So it's obviously better to have a large telescope. Now, where should you try and do your observations? Well, a smooth laminar flow is ideal, and the best places on Earth to have telescopes are on mountaintops facing the sea. So the sea, if the air currents have crossed the sea, flat, cool ocean, then that's the best place to place an observatory on top of a mountain on the sea side of the mountain. And I stole this from Damien Peach, and this is demonstrating that if you have a site there, site A, then Damien Peach can get an image of Jupiter like that because the air is stable and you can get a good image. But if you're on the other side of the mountain, then the flow is turbulent. The air has gone over the mountain and become turbulent. So the best even Damien Peach can do is this image here on the right. So it depends critically where you are. And it's quite easy to look and see about Dundee, and Dundee is actually quite poor. It's not the best because the wind direction tends to be like this all year round. It basically comes from the west or the west-southwest all the time. So it's coming over land in the direction of Perth. So it's not ideal. What we'd like is we could get a wind off the sea, then it might be better. But we can't do much about that. So Dundee is not a great place for astronomy. The other problem we have in the UK is the jet stream. And the jet stream causes some turbulence in the upper atmosphere and can make observations of the moon and the planets pretty difficult. Now, it's possible to go online and actually get a map of what the jet stream's doing. So this was last Tuesday, the 12th of January, and you can see here, if I just put in a pen here, you can see that the, you can see that the UK is here, and the jet stream is turning directly over the UK and causing lots of problems on Tuesday. So if you wanted to get some good images, then you would go to Iceland, for example, here, or you go to Spain. But you certainly wouldn't be in the UK and on the east coast of Scotland, because the jet stream is causing quite an issue there. And also Siberia would be good. Okay, if you want to try and measure the seeing conditions, then we go back to kind of basic performance of the telescope, and we talk about the Airy Disc. So if there's no atmosphere, a small star, which is a point source, obviously, would have a size which is the Airy Disc, which is determined by diffraction and is inversely proportional to the diameter of the telescope. So with a high magnification, this is what you get. I'll just go back to the arrow. With a high magnification, this is what you get. And if you have turbulence coming in, then the Airy Disc goes from just a small point and gets bigger and bigger and bigger until it gets a complete jumble. So if you look at a star with high magnification through a telescope with bad seeing, then you'll get something like this, which is moving around all the time and is really pretty hopeless. And obviously Hubble is in this condition here, and then Earth-based observation tends to be in this area here, where you get a large seeing disk, and people talk about the seeing disk, which is different from the Airy Disc because it's bigger and it's expanded by the turbulence effect. So if you want to do some measurements, then what people tend to do is take a plot across the seeing disk. So you take a line across here and you do a plot and you get something like this. Now, this example here wouldn't be like this because it would have lots of up and down. But if you did this one there, then you would get something like this, and you would take the half maximum and you would take this measurement, and people call it the full width half maximum. And that's how people tend to compare seeing measurements, by measuring the full width half maximum of the seeing disk. So you can do those kinds of measurements. And the measurements you get are in arc seconds. An arc second is 1 over 3,600 of an arc degree. Now, the Hubble telescope will give you a performance of about 0.1 arc seconds. So that's the kind of gold standard, if you like. And a good site on Earth will give you around about 1 arc second. And if you go to a mountain in Chile, which is obviously facing the sea and it's on the west, then you can get 0.4 arc seconds. But typically, we'll be experiencing something of 2 or 3 or even worse. So our performance tends to be, in comparison to the Hubble telescope, we'd be about 30, 40, 50 times worse. And that's why people go to these mountainous sites and strange places to get this kind of performance. Now, it's also possible to go to a website called Meteoblue and get a forecast. So this is Dundee today, and this is this evening. And you can see here that you can get the seeing forecast in arc seconds. So at the moment it would be about 1.57 arc seconds, which is not that bad. But the problem, you can also get the jet stream forecast, and you can see that after lunch today, the jet stream got really quite bad. So even though the seeing forecast lower down isn't too bad, the jet stream is extremely bad. And so if it wasn't cloudy, which it is, of course, we probably wouldn't get very good seeing tonight. So it is actually possible to get that information. Okay, so what's the solution to all this? Well, you can launch your own Hubble if you want to do that, or you can use lucky imaging, which I'll say something about, or you can do adaptive imaging. So lucky imaging is based on the idea that the atmosphere is turbulent, but now and again the seeing becomes quite good. And the coherence time associated with the seeing and changing is tens of milliseconds. So if you can take pictures with an exposure in the millisecond range, then it's possible now and again to get good images. Some of the time it will be worse, and some of the time it will be better. But if you take those images, then some of the images will be okay. So lucky imaging is basically recording many images with exposures in the millisecond range and selecting in software only the best images for further use. So that's the principle of lucky imaging. And these are some examples that I took. And if you look very closely, you can probably see that that one there is quite good. This one is not so good, and these are kind of single images. And if you take 1,000 frames and select maybe 50% or less and process those, then you can get something which is okay, which is pretty good. And you can achieve with this technique a full width half maximum of maybe 0.9 arc seconds. So that's equivalent to quite a good sight worldwide, really. So that's the principle of lucky imaging. And some people take thousands and thousands of frames and only take 10%, and 10% of thousands and thousands. If the 10% of the images are quite good, then you can get very good results. Okay, finally, to say something about adaptive imaging. Adaptive imaging is the idea of having a huge deformable mirror. So that's a mirror which can be bent, which is basically a plastic mirror, and it's got many servo motors on the back of it. And you can change the shape of the mirror to try and compensate for the turbulence. So if you use a laser or multiple lasers to measure the atmospheric turbulence, then you can automatically adjust the mirror to correct for the distortion of the wavefront. So this is a kind of schematic of what's happening. You've got an image which is distorted by turbulence. You've got a distorted wavefront here. You've got a mirror that you can change the shape of, and you've got a control system which controls that. So you measure the shape of the waveform of this system here, you correct it, and then the camera gives you a corrected image at the end of the day. So that's quite a complicated system, but it does give you extremely good results. So this is an example of Neptune, obviously not from me. And if you use adaptive optics on the telescope, you can get this result. If you don't have adaptive optics, that's what you get. So it's a very effective way of doing it. But it's seriously expensive. And it's only really professional observatories can do that. It can improve the resolution hugely, and you can get down to full width half maximum of 0.07, less than 0.07. And remember, Hubble was 0.1. So it's approaching the performance of Hubble. There are some advantages for Hubble still, because you can look at other wavelengths that you can't look at on the surface, but it can approach the same performance in terms of resolution. So in conclusion, if you win the lottery, and if you move to Chile, and if you buy adaptive optics, then you can get fantastic images. But otherwise, you just have to keep struggling with the seeing we've got. Thanks very much.
Struggling finding my mute buttons. Thanks, Richard. That was really great. Any comments or questions?
Can I ask one?
Yeah.
It's not specifically directed at that from the talk. It's to everybody. I wonder if anybody has used something called an apodizing screen. A lot of blank faces.
No, not knowingly.
It sounds like an antiseptic.
Not cream, Mike. Screen. No, it's something that I know a lot of older visual observers use in poor weather or poor seeing. So it's apposite to the conversation. It's of meshes like curtain mesh or very fine wire mesh that's laid across the front aperture of larger aperture telescopes with increasing density from inwards out, so that the outer section has much more density of the mesh than the inner section. And the theory behind it is that when you showed that excellent picture of the Airy Disc, it's through diffraction effects supposed to rob the energy from the outer rings of the Airy Disc, leaving the inner ring unaffected. So it apparently produces a sharper visual image. You lower the contrast, but you raise the focal quality, if you like, in poor seeing conditions. And now there are people who swear by them. I've never used one. I've always wondered whether they'd actually be useful for imaging in poor seeing conditions, or whether it was maybe an eye effect. So I just wondered if anybody had ever used one, but it looks like nobody's ever heard of one. So I'll shut up now.
No.
Any other comments for Richard?
Yeah, could I ask, the Meteoblue forecasting website is easy to find, is it?
Yeah. You just Google it.
Okay.
Just Google it, it comes up.
Another one that does something similar is called metcheck.com, METCHECK, metcheck.com. That, you just web search for that. That also has a hobbies drop down, and one of the hobbies drop down is astronomy, and you can then put in your locational postcode and it gives you an astronomy seeing forecast, very similar to what was it, Meteoblue.
Meteoblue, yeah.
Yeah, same sort of thing.
Great. Thanks for
I
that.
was wondering how big the mountain has to be to get Damien Peachey's beautiful image of Jupiter to change so dramatically. Does being at the bottom of the Sidlaws count, for example?
Well, I suspect it probably does. I mean, I suspect any mountain that the airflow goes over it is going to be turbulent on the other side. But I mean, obviously, Damien Peach produces images which nobody quite believes in some ways.
His are more vulnerable to effect than mine might be.
Yeah.
I think Damien has his own private Hubble up there. Some of the pictures that he produces.
He does tend to go to Barbados quite a lot as well.
Yeah, he does. That's right. Yeah.
This turbulence affecting the lee of a mountain is infamously bad in the west coast of America. They've got there's a program on a few nights ago about an appalling quantity of aircraft that drop out of the sky for apparently no reason until they sussed it, and it's simply the downdraft exceeds their rise ability and they simply fly into the ground.
Oh.
Nothing to do with astronomy, but the same phenomenon. You got a smooth flow coming off the Pacific, hits the Rockies, up it goes, and then it literally falls over the other side. And you get all sorts of effect, fogs, turbulent downdraft, and all sorts of things.
Yeah, Mike, if you fly a paraglider, you know about that.
Yeah.
Get downwind of the oncoming wind is very turbulent. It can be very nasty. On the other side, it's quite smooth.
I don't think I can do too much about the Sidlaws, but I could sort of go around the other side of the house or something.
Yeah.
Anybody else got any comments for Richard?
No, there's nothing on the YouTube chat either.
Okay.